Hello, and thank you for joining us. I'm Himani Gupta, Bioinformatics Analyst at Premier Biosoft. I'm here today to introduce this webinar entitled Informatics Support for MS Based Lipidomics Methods. Dr. Sanjeev Mehti, Chief Scientific Officer at Premier Biosoft, is joining us today as a presenter. We have allotted approximately half an hour for today's event. Before we get started, let me just remind you this is an interactive webinar, so we encourage you to participate by submitting as many questions as you want at any time during the presentation. Just type your question in the chat box that appears at the bottom of your screen and click send. We'll answer as many questions as the time permits in the Q&A session at the end of this 20-minute presentation. However, if we are unable to answer your questions today, we will answer them by email. Now it's my pleasure to introduce today's speaker. Dr. Sanjeev Mehti has over a decade of rich experience in algorithm design and data analysis. He is currently responsible for driving the development and commercialization of the mass spectrometry line of products at Premier Biosoft. He has been the person responsible for interfacing with key partners to co-market the products developed by the company. He coordinates research activities by collaborating with scientists from both academia and industry. He holds a PhD in statistics from Devi Ahilya University, Indore, India. He has received the prestigious Young Scientist Award in the field of mathematics, statistics, and computer science in the year 2010, conferred by the State Council of Science and Technology. His works have been published extensively in scientific journals and books. So let's begin with a very warm welcome to Dr. Sanjeev Mehti. Over to you, Dr. Mehti.
Thank you, Himani, for your introduction. Hi, everybody. Today, I want to start this talk by giving a brief introduction on our company's background. We, Premier Biosoft, have been developing software solutions to automate mass spectrometry-based omics analysis, namely glycomics, lipidomics, metabolomics, and proteomics. Today, I'm going to talk about what we have done till now to provide informatics support for mass spectrometry-based lipidomics methods. Lipidomics, defined as the large-scale study of pathways and networks of cellular lipids in biological systems, emerged in the early 2000s and has greatly advanced in recent years, largely due to the development of mass spectrometry techniques. Many novel applications of lipidomics in the fields of biological and biomedical research have been published extensively. Rapid advancement in the field of analytical technologies, particularly mass spectrometry and its complementary technologies such as liquid chromatography and ion mobility spectrometry, are fueling lipidomics research. Yang and Han 2016 published a comprehensive review of various techniques on mass spectrometry-based lipidomics techniques, their key features, advantages, and associated limitations. The challenges with lipidomics lie in the chemical complexity and large range of concentrations of thousands of lipid species present in biological samples. Besides, mass spectrometry-based lipidomics methods generate a large amount of data. Hence, manual annotations of mass spectra for lipid identification and quantitation is time-consuming and tedious. This necessitates development of sophisticated and robust bioinformatics tools to automate the process of data analysis. In the upcoming slides, I have listed some of the key challenges that hinder the development of comprehensive software suite for lipid identification and quantitation using data generated by various mass spectrometry-based lipidomics approaches. Challenge number 1, vendor-specific raw data file format. The problem with vendor-specific raw data file format is data from these different mass spectrometry instruments are non-communicable. As a solution, many XML-based format files such as MGXML, MGData, and MGML formats have been developed. However, one of the main drawbacks of this XML-based format file is when you convert a raw data file from its native format to an XML format file, the size of the data file on the hard drive of the computer increases multi-folds, sometimes up to 100 times the original size of the native file. This means that the processing of the data by extracting raw data from these XML format files is going to be time-consuming and memory-intensive that could severely limit the analysis capability of the software suite, especially when we are dealing with hundreds of biological and technical replicates that are very common in lipidomics analysis. Challenge number 2, data preprocessing methods. Data preprocessing includes peak detection, peak picking, molecular feature finding, and retention time alignment for LC-MS workflows. This is a necessary step before subjecting the mass spectrometric data to database search for lipid identification and quantitation. There are many data preprocessing methods depending on what mass spectrometry based lipidomics approach you have used. For example, data preprocessing method for direct infusion scanning experiments is different from data preprocessing method for direct infusion MS and MS-MS, MS-MS acquired using either DDA or DIA methods. Similarly, data preprocessing methods for LC-MS workflows is different from data preprocessing method for LC with ion mobility spectrometry MS workflows. Challenge number 3, overlapping isotopic clusters. This is one of the most frequently encountered challenges in mass spectrometry based lipidomic analysis. Overlapping isotopic clusters can not only bias the identification of lipid species but also bias the accurate quantities of lipids present in biological samples. In this slide, I have shown a typical mass spectrum in which 3 different species have overlapping isotopic envelopes. For accurate identification as well as accurate measurement of their abundances in biological sample, the software must have the ability to deconvolute these lipid species correctly. Challenge number 4, subclass specific fragmentation patterns. Automated interpretation of lipid MS-MS spectra is more challenging when compared to other biopolymers such as DNA, carbohydrates, or peptides. This is because lipids show much less standardized fragment mass spectra. Each lipid subclass has its own fragmentation pattern as well as ionization efficiency. In this slide, I have shown annotated MS-MS spectra of phospholipids from lipid maps standards, annotated MS spectra of cholesterols and wax monoesters from published literature. As a solution to the challenges I have listed above, we have been developing SimLipid softwares to provide a comprehensive software suite to automate lipid identification and subsequent quantitation using various mass spectrometry-based lipidomics approaches. Some of the key features of SimLipid include its ability to extract raw data directly from vendor-specific native file formats. For example, SimLipid can extract raw data from waters.raw file, Bruker's, BAP, YAP, FIT, and also it can extract MetaboEscape pick list from Bruker's MGF file format. SimLipid can also extract pick list directly from Agilent's Mass Hunter compound exchange format files. In addition to these native file formats, SimLipid also can extract raw data or pick lists from standard format files such as MGXML, MGData, Microsoft Excel, and text format files. Once the raw data files are loaded into SimLipid project, you can view the data. You have tabular view in which each row represents a scan in case of raw data or a detected compound in case of pick list. You also can view the total ion chromatogram, best peak chromatogram, or extracted ion chromatogram for a selected file. You have a spectrum view for a selected time point in chromatogram view or selected row in the tabular view. If you have performed database search for lipid identifications, identified lipids will be listed in the search result panel. Mass annotation panel will display annotated MS or MS-MS spectrum. For a selected lipid ID, lipid information panel will display additional lipid information. The main objective of this graphical user interface of SimLipid software is to facilitate users to visualize and review both the data as well as the results on a single workbench. SimLipid supports various data preprocessing methods. SimLipid can process data from LC-MS workflows, LC ion mobility MS workflows, Waters UHPLC sonar MS workflows, MS all workflows, and various direct infusion and DIA workflows. In this slide, I have shown typical graphical user interface of SimLipid software, showing generated pick list for Waters UHPLC sonar MS data file. For a selected compound in the pick list, SimLipid identified the lipid structure. The structure is being displayed here with detailed information in the lipid information panel. It also displays the time at which this lipid was identified in the total ion chromatogram. For this selected compound, you can visualize the extracted ion chromatogram in LC domain, extracted ion chromatogram in sonar domain, and overlay of extracted ion chromatograms for parent as well as the product ions in sonar domain. SimLipid identifies lipid structures by exact mass database source, product ion database source, or filters based on transition masses generated by precursor ion scanning or neutral loss scanning experiments. SimLipid database contains over 1.5 million structure-specific in silico fragment ions of over 40,000 lipid species. The database also stores over 5,000 transition masses for precursor ion scanning and neutral loss scanning experiments. The enterprise editions of SimLipid software is customizable. You can create custom database and store lipid structures along with retention time and CCS values specific to lipid species. SimLipid performs MS and MS database search for lipid identification in batch mode. In a single batch, you can submit 100,000 MS and MS scans. There is no limitations on the number of batches you can submit into SimLipid server program. SimLipid employs effective MS scoring algorithms for distinguishing isobaric lipid species based on product ion data. Here is an example how SimLipid distinguishes two isobaric lipid species, namely TG 18-2, 18-2, 25 and TG 18-2, 18-3, 24. For the first rank lipid species with unique fatty acid chains 18-2, 18-2 and 25, all the characteristic ions corresponding to these two fatty acid chains are observed in the MS spectrum. However, for the other lipid species, characteristic ion corresponding to only one of the fatty acid chains, that is 18-2, was observed in the MS spectrum. Another key functionality of SimLipid software is its ability to map lipids identified in variable ion modes. Here is an example of phosphoethylenomine with fatty acid chains 18-1, 16-0. In the positive mode experiment, characteristic ions corresponding to neutral loss of 141 from the parent ion species is observed. However, in the negative mode, we observe characteristic ions corresponding to fatty acid chains 18-1 and 16-0. SimLipid can combine these characteristic ions observed in variable ion modes and report this lipid as a confidently identified lipid species. SimLipid also supports interpretation of complex MS spectra. For example, MS spectra generated by multi-top workflows. SimLipid uses B ion, C ion, acylium ion in addition to charged remote fragment ions that could lead to distinguishing regioisomers. SimLipid provides comprehensive support for automated analysis of triple quadruple base precursor ion scanning and neutral loss scanning. For example, precursor ion scanning of 184 for phospholipids, profiling, and subsequent quantitation. After annotating peaks in the mass spectra with lipid species identified using MS data, SimLipid performs deconvolutions of lipid species with overlapping isotopic clusters. SimLipid then reports the corrected peak intensities of lipid species, thereby enabling accurate measurement of lipid abundances in biological samples. Another point I would like to cover in this talk is data normalization using abundances of internal standards. SimLipid normalizes the measured abundances of analytes in a sample with respect to abundances of the internal standards belonging to the SAM subclass. For example, all the 120 Tz lipids detected between 29 minutes and 41.7 minutes were normalized with respect to the abundance of the internal standard, that is Tg 170, 170, 170, as displayed in this screenshot. Similarly, all the PC lipids that were detected between 12.7 minutes and 24.7 minutes were normalized with respect to the internal standard PC 12013. If there are lipids that are detected with no matching internal standard belonging to the SAM subclass, for example, ceramide lipids that were detected between 29 minutes and 35 minutes, they were normalized using the closest retention time technique. This is a technique that normalizes the abundance of a particular analyte with respect to the abundance of internal standard of any subclass or class that was detected closest to the analyte in the retention time domain. For example, if I consider the lipid species ceramide lipid species at 35 minutes with no matching internal standard that has SAM subclass or belonging to the SAM subclass, TG 170, will be used as the internal standard. One of the main drawbacks of this closest retention time technique for data normalization is this technique does not work for flow injection analysis based lipidomics methods where there are no retention times. As a solution, SimLipid allows users to manually select a lipid of a class as the internal standard. However, the program does not verify if the selected lipid species is consistently detected across biological or technical replicates. The program currently supports data normalization using internal standards for Agilent's LC-MS-based workflows. Future work would look to improve the software so that this technique is extended for all other workflows. We are also working on developing a module that will allow lipids with no matching internal standards to be normalized automatically with respect to either average of the abundances of all the internal standards spiked into the sample or some abundances of all the lipids detected for the class. For example, if we do not have internal standard for the PC lipid subclass or class, then we use some abundances of all these detected PC lipid species to normalize the abundance of each and every PC analyte. This will make data normalization method applicable to all mass spectrometry based lipidomics methods that use either chromatography separation prior to mass spectrometry experiments or flow injection analysis mass spectrometry process. SimLipid provides various charts and tables to give an overview of lipid profiles and their comparison across biological replicates. Here are some of the typical pie charts and tables that are generated by SimLipid software after database search is completed. The table shows comparative analysis of number of lipid species specific to subclass between two experimental runs. SimLipid search results can be exported into Microsoft Excel file for further downstream analysis. For example, the structure-specific characteristic ions and their corresponding relative intensity observed in the MS-MS spectrum can be used for detailed investigation on whether a lipid species was identified based on characteristic ions corresponding to only head group or fatty acid chains. Here is an example, PC332. So using Microsoft Excel workflow we recommend for our customer, we can directly report these lipids as PC16171 because characteristic ions corresponding to fatty acid chain 16.1 as well as 17.1 were observed in the MS-MS spectrum. Finally, SimLipid results can also be directly exported into file formats that can be used as input file to statistical and pathway analysis software tools such as Mass Profiler Professional from Agilent, MetaboAnalyst from GeoLab, McGill University, and MetaboEscape 4.0 and higher versions from Bruker. With this, I want to thank Dr. Vladimir Shulap, Professor, Department of Biological Sciences, University of North Texas, Denton, for his valuable help and feedback in creating this webinar. Thank you very much.
Thank you, Dr. Mehti, for the insightful talk. It's now time for the question and answer session. We are now going to begin answering the questions submitted during the presentation. As a reminder, you can still submit questions to the chat box. We have a number of interesting questions, so I will move straight on to those. The first question is, some software packages have the ability to identify popular deuterium labeled internal standards. Example, Avanti Splash Lipidomics. Do newer versions of SimLipid have automated internal standard identification features?
Okay, that's a very good question. Yes, the answer is yes. SimLipid, we have already included Splash lipidomics standards into SimLipid database. So when you run database search, those deuterated lipids will automatically be identified. So in addition to these deuterated lipids, if you have any synthetic lipids or any standards you have created on your own or you have purchased from other organization other than this Splash Avanti people, you can create a custom database of those deuterated or synthetic lipids to be used as internal standards.
Okay, thank you. The next question is, can you create an LC-MS template for lipid identification using SimLipid?
Yes, the answer is yes. We can create a LC-MS template for lipid identification. SimLipid Enterprise Edition allows users to create custom database by storing lipid structures along with retention times and CCS values. These custom database can further be used for lipid identification by performing MS or MS-MS search by using this precursor MG or exact mass, as well as the retention time as the initial source predicates. So yes, the answer is yes. You can create LCMS templates for lipid identification using SimLipid software.
Okay. Next question is, how accurate is the fragmentation matching and can they be correlated to biological source such as dietary, microbial, or animal?
Okay, so how accurate this ID? So lipid identified by SimLipid is as accurate as what mass spectrometry workflow you people are using. So you have a depending on if you have a very good sample, if you have a very good MS spectra, MS data, then definitely SimLipid is going to identify those lipids very correctly and which can be annotated back to all those biological sources. So it depends on how you ran the experiments and how what kind of data you have.
The next question is, I would like to ask about the basis of scoring. Is it very much different with SimGlycan scoring?
Very good question. So we do have a software called SimGlycan for glycan identification, uh, and yes, very much different, because when you look into glycan, the fragmentation pattern is simple. For each and every glycan molecule, the fragmentation pattern is always going to be the way how it is. Like we generate glycoside cross ring or cross ring fragments. But as I mentioned in my talk, lipid fragmentation is very different. Each and every subclass has their own fragmentation pattern, as well as it varies uh, between ion modes. So when we consider this fragmentation pattern as well as ionization efficiency into scoring, the scoring mechanism is very different from how we use in glycan identification as compared to what we use in lipid identification.
All right. So the next question is, can we analyze water's MSC workflow using SimLipid software?
Yes, in 6.05, we are coming out it is not available in the market, but we have already completed the testing. We are about to come out with that one. So yes, SimLipid can perform peak picking, peak detections, uh, molecular feature finding, and these deconvolutions of this one extractor and chromatogram for isomeric lipids, for this MS Waters MS to the E workflow.
The other question is, you mentioned for the co-eluting lipid, the software is able to calculate each lipid contribution separately. I was wondering, how does the software handle this?
Okay, so uh, that is a very good question. As a matter of fact, we have been working on uh, separating these coeluting lipids as well as measuring them accurately, using various techniques. So the first one is, if you use LCMS workflow, definitely, we try to deconvolute as much as possible by, using algorithmic deconvolutions of you know, uh, those convoluted peaks. Another technique we use is we use fragment ion intensity to measure the lipids. Okay, so say PE phosphoethylenomin and PC lipid, you know may not be separable because they might have same mass, and especially when we use DIA settings, then definitely there is no way we can separate those out. So what we do is we identify phosphoethylenomin lipid as well as the phosphocholine lipid using MSMS data, and we look into the MSMS spectrum and find out what fragment ion correspond to the PC lipid and what fragment ion correspond to the PE lipid. And once these are separated out, then we sum up the observed intensities of all those fragment ion corresponding to the PC, and this is used as the measure of abundance or abundance of the PC lipid. And similarly for PE lipid also, we measure the abundance of that particular PE lipid species by summing up the abundance of all those fragment ion corresponding to the phosphoethylenomin lipid. So again, this is a very interesting questions, and a very interesting area where we are also continuously working on. And we everybody is welcome to evaluate our software and have a detailed discussion on what we are doing and how we can further improve this particular measurement.
Another question is, the delta mass for identified lipids is quite high between the theoretical MZ and experimental. How do you explain it? How accurate are the IDs?
Okay, so okay, so this question, let me understand it now from my perspective. What my understanding you are saying is that when you use low resolution mass spectrometry workflow, then delta mass could be very different in a very large, like what you have as a theoretical mg and what you have as the observed mg. Definitely it may be quite uh, quite large. So for the for this low resolution workflow, what we employ is not only on the MSMS data, but once lipids are identified, we annotate those identified lipid back onto the MS1 peaks, and then we perform this one isotopic overlapping uh, correction, so that as much as possible we deconvolute if there is any isotopic influence between those nearby lipids. So for high resolution mass spectrometry workflow, this isotopic overlapping still happens. It doesn't, in high resolution doesn't mean that you are not going to see this isotopic overlapping. So yes, it does happen, but the delta mass is not going to be that large. We sometimes we use like 5 ppm, especially for high resolution accurate mass MS instruments such as Orbitrap or QTOP instruments. And even for FTICR mass spectrometry workflows, we have used 2 ppm the delta mass as the maximum tolerance for lipid identification. So it varies between what instrument you are using, but yes, we also provide
Sorry,
some measures to
sorry to
you know
interrupt, Sanjeev. The person said that they were using high resolution MS.
high resolution MS. So okay, in that case, you know I'm not sure about which instrument he is using or she is using, but my understanding is that we generally use at the most 10 ppm for high resolution mass spectrometry workflows. And if it is Orbitrap, generally we prefer 5 ppm tolerance for both product and precursor mg values, mg ions.
Okay. Next question is, do newer versions of SimLipid have statistical analysis tools such as principal component analysis in untargeted lipidomics workflows?
Okay, very interesting. And the second last slide, that is the whole reason why we developed a module which can directly export SimLipid results into a format that is directly compatible with popular statistical analysis software. So one of the most interesting software we use and we map it directly compatible is Metabo Analyst software from Zia Lab, McGill University. So you perform lipid identification, you can perform peak picking, peak detection, lipid identification, alignment, and everything in SimLipid. Once lipids are identified accurately and you are satisfied with the results of the SimLipid, you can export directly into CSV file format, which is actually the prescribed format of Metabo Analyst software. So you don't need to do anything. You just go to the Metabo Analyst software, browse the file exported by SimLipid results, use that as an input file, and you can perform all the statistical analysis such as principal component analysis, hierarchical cluster analysis, even all those PLSDA analysis, orthogonal PLSD, all those statistical analysis are available there. So direct compatibility is provided instead of SimLipid doing on its own.
Okay. So we are able to take one more question. The last question will be, I would like to use the demo version of the SimLipid. How long can I use the demo version?
Okay, so that our technical support team is better equipped to answer that. They are the people who handle that kind of questions. But I believe you can, as far as I understand, I think you can use for generally 15 days, or you can extend it for another, like 7 days if if you could not complete the analysis. So please write to our support team, support@premierbiosoft.com. We have a very nice technical support line online, always available. You can chat, you can write, you can call. So have a request a demo versions of SimLipid software and evaluate it, and send us the feedback.
All right, we are running out of time, so I need to conclude the QA session. For those whose questions have not been answered, we will reply through email as soon as possible. Today's webinar has been recorded and will be available for viewing in the next few days. We will send you an email with link to access the recorded webinar. Also, once the webinar ends, a feedback box will appear on your screen. If you have any more questions or comments that you wish to put across Dr. Methi, please enter them in the feedback box and he will get back to you by email. So this concludes today's webinar. On behalf of our speaker, Dr. Sanjeev Methi, and me, Himani Gupta, it's goodbye for now. Have a great day ahead and thank you so much for attending.
Thank you for attending. Bye-bye.